we want to define the idea of torque and explain why it makes sense. So let's consider a rigid body here. This is kind of looks like a strap, the kind we rotate, but it could have any shape as long as it has an axis of rotation, and of course it has a moment of inertia. And we're going to leave all those things unspecified because none of this at this point, or the definition of torque doesn't require anything about moment of inertia. It interacts with moment of inertia in a way we'll see. So we have a body rotating about some axis. Okay, it could be any body rotating about any axis. Now, we have a force F1 acting on that body, and the vector from the axis of rotation to the point of application of the force is going to be the R1 vector. And we're going to assume for the moment that F1 is perpendicular to R1. Now here we have a force F2 acting on the same object with the vector from the axis to the point of application being R2. And we're going to assume the body goes through the same delta theta. We're going to consider what work this force does, what work this force does as the body rotates through an angle delta theta. And same angle in both cases. So we have F1 at R1, F1 perpendicular to R1, F2 at R2, F2 perpendicular to R2, and the same delta theta. Now the work done in the first case is F1 delta S1. We assume that the force F1 remains perpendicular to the R vector as the object rotates, and the same with the vector with the force R2. In that case, then the work done by force F1 through delta theta 1, well, it's going to be F1 times delta S1. The force 1 acts through the distance equal to the arc to the arc length, or to the length of this arc. Okay, and F2 acts through distance equal to the length of this arc. Now we know that delta S1 is just the radius of this partial circle times the angle, so that F1 delta S1 becomes F1 R1 delta theta, and the work on the second is F2 R2 delta theta. Delta S1 is R1 delta theta, delta S2 is R2 delta theta. Now, the forces will have the same effect on the velocity omega, angular velocity omega, if and only if the work done by the first force is equal to the work done by the second force. Let's say on the kinetic energy. Okay? So that's a little safer than omega. We haven't specified an initial velocity. And that would make a difference. I'd have to qualify the argument quite a bit more if I wanted to talk about just the effect on omega. But same effect on the kinetic energy of the system if delta W1 equals delta W2. Well, delta W1 equals delta W2 means F1 R1 delta theta equals F2 R2 delta theta. Now, if we let tau 1 equal F1 R1, tau 2 equal F2 R2, then this equation becomes tau 1 delta theta equals tau 2 delta theta so tau 1 equals tau 2. And that's what we're going to call the torque. So the work-kinetic energy relationship motivates this definition of torque. There are other ways to motivate the definition. I think your textbook uses a slightly different approach, but it's completely equivalent. So we can define the torque of a force F at a distance r from the axis provided for the moment that the r vector is perpendicular to the f vector as torque equals r times f. Now, f is not always going to be perpendicular to r. If f isn't perpendicular to r, then we have to modify the definition, extend the definition a little bit. For this case, this is the torque, but we have a more general definition of torque, and we're going to take a look at that. So let's think about the same situation. We have an f vector here that is not necessarily perpendicular to the r vector. Incidentally, the r vectors might have been a little difficult to see before, but here's the r1 vector, here's the r2 vector. Okay, now, if this is the r vector and this is the f vector, then, of course, the f vector can be replaced by its components parallel and perpendicular to the r vector. So we have now f perpendicular and f parallel, and we replace the vector f with those components, and it should be clear that the f parallel does no work on the system because the system can't move in the direction of f parallel. So there's zero motion. Now f parallel will have the effect of pulling on the object, which in turn pulls on whatever axle we have or whatever we have constraining this object to rotate about this axis. But we see that the work, if we go through an angle theta, and I'm not going to attempt to draw that, through an angle delta theta, the work is, in this case, going to be f perpendicular delta s, which is going to be f perpendicular times r delta theta. So we're going to define the torque here to be for some reason I wrote an r there as opposed to perpendicular. F perpendicular, shouldn't have tried to squeeze that in, times r, in which case delta W equals torque times delta theta. So now we have magnitude of the torque is F perpendicular times r, And of course, if we've got an angle theta between R and F, then we can use sines and cosines to get the parallel and perpendicular components, and that's all very straightforward. Now we're going to continue in another clip to further generalize this definition of torque.